Okay, on to part two. Let's talk about how we really do things most of the time, which is with skeletal hierarchies. All right, so what do we really do? The artist makes that mesh that we just talked about with all those vertices, but then inside that mesh, we'll put in a skeleton. We'll put in a skeletal hierarchy. That's these bones. All these colored little stick shapes are the bones, and they are connected in a hierarchical fashion, just like, just like you'd expect. The foot bone is connected to the heel bone, and the heel bone is connected to the knee bone, and the knee bone is connected to the hip bone, and the hip bone is connected to the spine bone. You get the point. And then what we'll do is we'll say that, this vertex right here, these vertices are associated with this bone right there. So when we move the bone, all the vertices that go with it, they're connected to it and they move together. Okay, a little vocab word. I've already been using this word quite a bit, and I think you figured out what it means, a pose. A pose is like a static position. We've got a skeleton here, and he's got this pose where this arm is down with the palm facing us, and this arm is outstretched with the palm facing us. That's his current pose. The way we're going to do animation is by going through a series of poses, just like you would with a flipbook animation, right? The artist would draw the character in a particular pose and then go to the next page, and the pose is very slightly different, and then the next page very slightly different. And it takes several pages of the flipbook to get to a more extreme part of the pose, and that's what we're going to do as well. Okay, now since we have bones instead of just the vertices, we don't actually store where all the vertices are in each pose. Instead, what we'll do is we will store where all the bones are in each pose. And then because we've got an association between the vertices and the bones, by moving the bones through their poses, we can get the vertices to move with them. All right, so what are we going to store? A bone can scale, maybe. It definitely rotates. We do lots of rotation, and sometimes it translates. So you can think of a rotation just like, look at your shoulder. You want to raise your arm. You do that by rotating your shoulder bone. Simple. Human beings mostly don't scale, but cartoons do. Like when the coyote gets hit on the head with the anvil, we'll compress his bones in one axis and stretch them in another axis, and then now he's all squashed and stretched. So that, depending on your game engine, you may or may not support scale. And then translation, real bones don't tend to do this, but sometimes it's convenient, to express a bone as a translation as opposed to it being a rotation. Let me give you an example. An eyebrow. I want to raise the eyebrows on my character's face. I don't want to do it with blend shapes. I want to do it with bones. So maybe I'll make an eyebrow bone, and I'm not going to make the artist have to try to calculate the rotation that's necessary to make that happen. Let's just let the artist lift that bone straight up, and that'll be a translation. Simple. Okay, now we have scale, rotation, and translation, and as we know, we can encode that as a matrix. And so that's what we'll be doing. We'll take that scale, translation, rotation, turn that into a matrix. Now, the skeleton was a hierarchy, we said. So that means there's the bone, and it's connected to a parent bone. We'll call that the child is connected to the parent, like the foot is connected to the leg. So when the foot bone is rotated, it's rotating relative to the leg, okay? Or we'll say it's moving in the space of the parent bone. So let's do that with an arm here. Try to visualize with me. Stick your arm straight out to the side. And if you bend your elbow by 90 degrees, now you've got your arm out to the side with your elbow bent. Now hold that elbow straight. Hold it bent. Don't let it move. And now move your shoulder around and you'll see what I'm talking about. The elbow joint is parented to the shoulder joint. So if the shoulder joint moves, the elbow goes with it. And that goes all the way down the entire bone chain. All right, so we are going to store the transform for each individual bone. As I mentioned, we're going to have rotation, we'll have translation, and possibly we'll have scale. You know, sometimes we just don't support scale. Sometimes we're going to support a fully three-dimensional scale. Like if you want the Roadrunner the Wile E. Coyote, you want him to squish. That means he has to squash on one axis and stretch on a different axis. Or maybe you just want to support growing and shrinking, and so just a float scale would be possible. Or, you know, maybe your engine is based on real-world, realistic characters and they don't scale. So we just don't need that at all. So that's what we will store. We'll store something like this for each bone, for each pose, and that's how we'll do it. And then we'll take this transform type of structure and we'll create a matrix out of it. And then when we have a matrix and we have the hierarchy, we can build for a particular bone, and this is the foot bone here. For a particular bone, the foot bone in the current pose, the matrix transform is given by this expression where we take in this pose the foot's matrix times the heels matrix in this pose, times the knee matrix in this pose, times the hip matrix, times the spine matrix. And you multiply all those out, and what we'll have is, in the end, a matrix, the C matrix, that transforms a vertex from foot space all the way out into model space, accounting for all the rotations and translations of this pose. Now you may be asking yourself, why don't I just store this as a matrix? Why do I need to keep the quaternions and the vectors? Why not a matrix? The answer is because we're going to be doing a lot of interpolation. And the quaternion in particular is specifically designed to let us do those blends and interpolations without screwing things up. Okay, so about that hierarchy. What we'll probably do is just make an array or a vector of all the different bones. And then what we'll need is to maintain the connections between the bones. Which one's the parent, which one's the child. And the simplest way to do that is to simply keep the index of the parent in each child bone. So for example, here we have, let's look at the hip, the left hip, or hip L. It points to its parent. It says that its parent index is index 1, which is the spine bone. And the spine bone's parent index is bone 0, which is the root bone. And so that's how we'll do it. And by doing that, we'll be able to, reconstruct the hierarchy and always know which bone is your parent, so that you can multiply those matrices in the correct order. Okay, so each bone moves in the space of its parent. So to take the chain all the way out to model space, remember all of our shaders are going to run in model space, right? And all of our vertices were created in model space. So how are we going to get back out to model space? Well, we'll need to apply the rotations and the animations for this particular frame, this pose, to get you from the current bone you're in out to the parent bone. And so like we'll go hip up to spine, and then spine up to root, and maybe that one's been animated. And maybe the artist has the ability to move this root bone too. And so we'll have to apply a matrix for the root to get out to model space. We'll chain those together, and now we have the vertex after it's been animated in model space. And we get there by multiplying up the chain. Now, before you jump to any conclusions that we're going to have like a for loop that we're going to go up the parent chain explicitly, let me point out there's a trick we'll get to in a bit where you actually only need to multiply times your parents because the rest of the chain's already been evaluated. But let's save that for a minute. Let's talk first about the bind pose. Sometimes called the T pose or the Da Vinci pose, and you can see why. This is the pose that the artist originally made the mesh in. Now they tend to use a pose kind of like this so that they can gain access to all the different parts. Like you can put the texture on the character's armpits and stuff, and you don't have to try to unfold it in order to get in there. So they'll make this very neutral pose where they can access all the vertices, and then they'll put the skeleton into this mesh. And the skeleton then forms the bind pose. This is the pose the skeleton was in when it was bound to the model. And that'll be considered the no animation pose. So if we apply 0 animation, we just bring in the character, this is what it'll look like. All right, so we've got our mesh, we've put our bones in it. When we put those bones in the original position, you'll see that they're not all just aligned like Z forward or X forward or whatever rest space. There's an offset between the bones, clearly. I mean, this bone starts here and the next bone starts here. So that'll be expressed as an offset from the origin of the other bone. That's a translation. And also there's a rotation. So like this bone is maybe pointing this way and this bone is pointing this way. And we'll take that original rotation and that original translation, and that we could build into a matrix. So that's the original local matrix for that bone. And from that, we can make the bind pose matrix. The bind pose matrix is the matrix that the skeleton was put into in the bind pose. And specifically, it's the one that takes us from joint space all the way out into model space. Now, the bone's local transform goes from bone space to parent space. Now that bone's parent space, like it goes from the upper arm space into the clavicle space, right? It goes from one space up the hierarchy. But for this bind pose matrix we just said, we wanted to go from bone space all the way out to model space. Okay, so for that, and I'm sure we're going to cover this, we'll cover this more in a bit, but for that, ostensibly what you need to do is take the local bind matrix of this bone and then multiply times its parent bind matrix. Then multiply times its parent, times its parent, times its parent, all the way out until you're in model space. Now, I'm planning to cover this, but I want to stress it because people get tripped up on this all the time. If you do it in a particular order, you don't have to go all the way up the chain every time. Instead of going from child to parent, child to parent, up to parent, up to parent, up to parent, let's calculate them in the opposite order. Let's start with the root object, and it has no parent. So the root object's bind matrix is just the bind matrix of that object. So let's go to the next one. Let's say the spine is next. So the spine's local matrix, we calculate it, and then we multiply that times the root object's matrix. Well, what is the root object's matrix? That's the one we just calculated, so it's available. We just use that one and multiply those two. Okay, let's go up to the next spine. I'll call it like spine 2. Spine 2, we calculate the local matrix, and then what we need to do is multiply that times spine 1's matrix times the root matrix. Well, what did we just calculate? We just calculated spine 1 times root. We just did that. So that means it's available. Just grab that one and use it. So that's what we'll be doing instead of doing this with a nested for loop where we go through each bone and then for each bone go through the whole chain. What we do is we'll go through each bone realizing that by the time we get to a child bone, we have already calculated its parent chain. The whole parent chain of the parent of that bone's already been calculated. Okay. We'll try and cover that more later.